Hi everyone, this is part 1 of our material on decision rules and error correction. An important question that lies before us is as follows. How does the receiver of a transmitted message avoid misinterpretation due to transmission error? For an example of what we might mean by this, let's suppose we have an alphabet S consisting of sell, buy, and no action, with an associated binary code C consisting of these 6-digit binary strings. So let's suppose we have a sender who wants to send the message buy. Well, first the sender encodes the message as 111111 and then puts this into a channel. Now, in the channel, there can be some transmission error. So what comes out may not be what the sender put in. So let's suppose what comes out is, this binary string with 4 1s and 2 zeros at the end. The receiver then takes this string and realizes that this is not one of the code words. So he or she must then make a decision. That is, apply some method where they choose one of the code words that they think corresponds to this message. So here the receiver has decided that this was the intended code word. And here all is well, right? Because the receiver also got the message buy, which was the intended message. Now, in the bottom row, something different happens, right? So again, we have the sender who wants to buy. He or she encodes this message as this string consisting of all ones, puts it in the channel, and of course, it's a noisy channel, so there may be some errors, and the string that comes out is this string. And notice that that string is not a code word, so the receiver then must take that string and decide what code word to use. And in this case, the receiver decides that this is the intended code word, which corresponds to no action. Now here we have a failure of sorts, right? The sender has sent the message buy. The receiver has interpreted this as no action. And so this is what we call a mistake. And we want to avoid those if possible. So this story of correcting transmission errors is one that is going to span the next few chapters. At the outset, there are several important characters in our story. The first is a binary code. Now, these binary codes are all going to be strings of length n. So all of the code words will have the same length. We'll also be dealing with a channel, right? We will have a sender who encodes a message and then puts it into a channel for a receiver to receive. The inputs and outputs of these channels will be binary strings of a fixed length n. And then finally, we have this idea of a decision rule. So a receiver will receive a string of length n from the channel and will then have to decide which code word to associate to that string. And the method that the receiver uses to associate code words to received strings is what's called a decision rule. Now, a mistake occurs when the decision rule fails to recover the intended code word. So that is the thing that we most want to avoid. So the idea is to pair our code C and our decision rule sigma in such a way that the likelihood of mistakes is reduced. So on the previous slide, we saw that decision rules are an important factor in error correction. Remember that a decision rule is a means by which a receiver will take a received string and decide which code word should be assigned to it. So as we proceed through this video, we'll be talking about a specific decision rule called the minimum distance rule. Now, as the name suggests, we will need to know how to measure distance between strings in Bn. So let's suppose we have a couple of strings, x and y, binary strings, both of length n. We can measure something called the Hamming distance between them. So to measure that distance, what we do is we just simply count the number of places where x and y differ. Now that we have this Hamming distance in hand, we can make what's called a radius r neighborhood of any given string. So we start with a string x and a number r that's bigger than or equal to 0. And what we do is we identify all of the strings, all of the binary strings of length n that are of distance less than or equal to r from x. So certainly this neighborhood will contain x itself, right? So if you want to sort of picture this in Euclidean terms, you can think about x as this string, and then this neighborhood is all of the strings that are of distance r or less from x. Okay, here we're going to get a little bit of practice using the Hamming distance and in computing some of these neighborhoods. In part A, we want to know the distance between 1, 0, 1, 1, 0 and 0, 1, 1, 0, 1. So what we want to do is count up all of the places where these two strings differ. So they differ in the first slot, they differ in the second slot, they are identical in the third slot, they differ in the fourth slot, and they differ in the fifth slot. So I count up the number of places where they differ, and there are 4 places. So this distance, the Hamming distance between those strings, is equal to 4. In part B, we're asked to compute some neighborhoods. Now, first, we're computing this neighborhood of radius 0 of our string 1, 0, 1, 1, 0. So that is going to consist of all strings that are of distance less than or equal to 0 from our given string. Now, it turns out there's only one string of distance less than or equal to 0 from our original string, and that's the original string itself. Now, the neighborhood of radius 1 of our given string, that is the collection of all strings of distance less than or equal to 1 from the given string. Certainly, it will contain our original string, right? Because that's of distance 0 from the original string. And now we're going to add on to that all of the strings that are of distance exactly 1 from the given string. And those should be and finally, right, so there's one element in our first neighborhood of radius 0. Our neighborhood of radius 1 will have, of course, our neighborhood of radius 0 together with all of the strings that are of distance exactly 1 from our given string. So there will be 1, 2, 3, 4, 5, 6. So there are 6 things here. Now, we've handled these 2 neighborhoods, and then we come to this neighborhood. So those are all of the strings that are of distance less than or equal to 2 from our original string 1, 0, 1, 1, 0. So what I would encourage you to do right now is see if you can write down all of those strings and then try to count them. So we will learn a little bit more about how to count elements in these neighborhoods a little bit later. But right now, if you could pause the video and see if you can write down all of the strings of distance 2 from our given string and count how many things are in that neighborhood. Here we list a couple of useful facts about the Hamming distance on binary strings of length n. The first is that d is what we call a metric on bn. That is, it behaves like we would expect a measure of distance to behave. First of all, the distance between any string and itself is 0, right? That should make sense. And the distance function is symmetric. That is, the distance from x to y is the same as the distance from y to x. And then finally, we have this thing called the triangle inequality, which says that the distance between any two strings is less than the sum of the distance from x to a third string plus the distance from that third string to z. Right, so you can sort of think about it visually like this. If this is x and z, then, you know, the distance between x and z should be less than or equal to the distance from x to some y added on to the distance from y to z. Okay, so all three of these are satisfied, and in your exercises, you'll be verifying these things. Okay, the other thing that's useful to know about the Hamming distance is how many objects are in a given neighborhood. So remember, on the last slide, we had an example where we were trying to compute elements in some of these neighborhoods, and I had asked you to count up how many elements were in each neighborhood. So generally speaking, if you want the size of a neighborhood of radius r of any given string, if the strings are in Bn, it's just going to be the sum n choose 0 plus n choose 1 up through n choose r. So I want you to remember here now that n choose k is this formula involving factorials, right? It's n factorial over k factorial times n minus k factorial. All right, now why should this be the case? So imagine we have a string x, and it's x1, x2, you know, down through x sub n. This neighborhood consists of all of the strings that are of distance r or less from x. So that's going to be the set of strings of distance exactly 0 from x, together with the strings of distance exactly 1 from x, together with the strings of distance exactly 2 from x, up until you get to the strings of distance exactly r from x. Now, how do I count, like, the number of strings exactly 2, of distance exactly 2 from x? Well, I start with my original string x, and then what I've got to do is pick two locations in here, say here and here, where I might change those bits from zeros to ones or vice versa to get another string y that differs from x in exactly 2 places. So the act of choosing those 2 slots, how many ways can I do that? Well, I have n slots altogether, and I'm choosing 2 of them to flip the bits, so it's n choose 2 altogether. Now, there's nothing special about 2. It could be 1 or 3 or whatever. And so the number of strings of distance, of any fixed distance from x is given by n choose that fixed distance. So we just add up all those fixed number of ways to choose the slots, and that should give us the size of the neighborhood. So now you should go back and think about this example on the previous slide. Remember, I asked you to find the size of N2 of, I think it was 10110. And if you came up with 16, then that's the right answer, because according to our formula, it should have been 5 choose 0 plus 5 choose 1 plus 5 choose 2, and that's 1 plus 5 plus 10, which is 16. Okay, now we're ready to introduce the minimum distance rule, which is a type of decision rule. So we start with a binary code C where all the code words have the same length n, and we have received a string Z, also of length n, in transmission. So we're going to let sigma of Z be a code word, C, so that the distance between Z and C is minimal. Now, this type of decision rule makes perfect sense, right? If you receive a string Z in transmission, it would make sense that you would assign it to a code word that is close to what was received. All right, so here we have an example. So here our code is going to consist of strings of length 5 that have exactly 2 ones. So if we try to list these down here, we might have 1 1 0 0 0, and then 1 0 1 0 0, 1 0 0 1 0, 1 0 0 0 1, and then 0 1 1 0 0, 1 0 1 0 0 1 0 0 1, and then 0 0 1 1 0 0. Actually, that last 0 shouldn't be there. 0 0 1 0 1, 0 0 0 1 1. That should be all of them. Where here again, that should not be there. Okay, so let's count how many we've got and make sure we've got them all. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that looks right? Because if you look at strings of length 5, you have to choose 2 slots to put the 1. 5 choose 2 is equal to 10. Okay, so we have got all of these code words now that live in C. And the next, in item B, we're asked, is this C equal to the neighborhood of radius 2 centered at 0, 0, 0, 0, 0? Well, the answer is no, right? Because that neighborhood consists of all strings that are not only of distance 2 from 0, 0, 0, 0, 0, but also things that are of distance less than 2. So for instance, the string consisting of all zeros is in this neighborhood, but it is not a code word. All right, so now let's apply this minimum distance rule to some strings. So let's suppose you as a receiver receive string 11000 in transmission, and you are looking for a code word that is as close as possible to that received word. Well, what would you choose? Well, 11000 is itself a code word. And so the distance between this received word and the code word, 11000, that distance is equal to 0. We can't do any better than that. Okay, now what about sigma of 10000? Well, that string is not a code word. So now I'm going to be looking for a code word that is as close as possible to this. And, well, one possibility might be 11000. That is of distance 1 from the received string. But the problem is that there are other code words, like 10100, that are also of distance 1 away from the received string. And so this raises a question. Well, which of those code words, both of which are of distance 1 from the received string, should we choose? So now what you should do is ask yourself what code word or code words are of minimum distance from the received string consisting of all ones. Okay, so anyway, the complication here is that if you have a received string, there may be more than one code word that is of minimum distance from that received string. Okay, so we're going to file that complication away for the moment and go on to part D. So part D asks, well, if C and C prime are distinct code words, what is the smallest possible distance between code words? So we go back up to part A and we look at our list of code words. And I see, for instance, that the distance between these two code words, these two first code words, is equal to 2. And if I go along and I look at all of the different pairs of code words, I am not able to find a pair of code words that has any distance smaller than 2. Right, so if you take any two distinct code words, their distance from each other is 2 or larger. Okay, this minimum distance that we computed in the last part of the previous example, that is an important quantity. And we're going to denote that quantity by the Greek letter delta. So again, that's the minimum Hamming distance between two distinct code words. Now, in the previous example, that minimum distance was equal to 2. All right, here we have a lemma that turns out to be rather important. What it says is that if this minimum distance is bigger than or equal to 2r plus 1, then the neighborhoods of radius r centered at C and C prime are disjoint whenever C and C prime are distinct code words. Now, disjoint, remember, means that they have nothing in common, meaning their intersection is empty. Okay, so let's go ahead and prove this lemma. So the best way, for this particular lemma, the best way to prove it is by contrapositive. So what that means is that we are going to assume that the neighborhoods are not disjoint, meaning that they do have something in common, and we're going to show that the minimum distance must be strictly less than 2r plus 1. So we're going to let x be a string that is in the intersection of these two neighborhoods. we're assuming now that they do have something in common. Then what do I know? Well, if I take the distance between C and C prime, then by the triangle inequality, that's less than or equal to the distance between C and X added to the distance between X and C prime. But remember that X is in both of these neighborhoods of radius r, which means that the distance from C to X and the distance from C prime to X, both of those distances are less than or equal to r. And so that means that this distance is strictly less than 2r plus 1. Now, if this particular distance between two distinct code words is less than 2r plus 1, that means that the minimum overall distance must also be less than 2r plus 1. And that proves the theorem. So we can use the previous lemma to prove this important coding theorem. So we suppose that we have a code, a binary code, on strings of length n, and that no more than r bit errors occur when transmitting code words. If the minimum distance of this code is bigger than or equal to 2 times r plus 1, then no mistakes occur when applying the minimum decision rule. So let's prove this theorem. So let's suppose we have a code word, C, and that's transmitted through our channel. And meanwhile, let's suppose that string Z is received. Now, the hypothesis tells us that no more than r bit errors have been committed when we send C through the channel. So by the hypothesis, we know that the Hamming distance between Z and C is less than or equal to r, right? So meanwhile, by the lemma, so the lemma tells us that the distance, the Hamming distance between Z and C prime is strictly bigger than r for C prime not equal to C. Right, now why is that? Well, if there were a C prime where the distance from Z to C prime were less than or equal to r, then that would tell us that the neighborhoods of radius r centered at C and C prime would have something in common, namely this Z, but we know from the lemma that that can't happen when the minimum distance is bigger than or equal to 2r plus 1. Okay, so now what does this tell us? If we apply the minimum decision rule, right, to z, what does that mean? Well, we're going to look for a code word that is as close as possible to z, and there's only one that is as close as possible, and that's this code word c. All other code words are further away than c is. And c is exactly the code word that we started with. So no mistakes are made. Right, so the upshot here, there are several points to be made here. The first is that there is no ambiguity about which code word to choose to assign to z. And further, the code word that we choose, the one that's closest to z, is exactly the right code word, right? It's the one that we started with. Another thing to keep in mind here is what is making all of this work? Well, it is the fact that this minimum distance in the code is large enough, meaning that the code words are not too close together, okay? Okay, so codes like this where the code words are not too close together are called error correcting codes. In particular, if the minimum distance delta is bigger than or equal to 2r plus 1, then the code is called an R error correcting code. Okay, here we have an example involving error correcting codes. So in part A, we're supposed to find a one error correcting code on binary strings of length 5 that has 3 code words. So here, we're just going to go by trial and error and see what happens. So let's let our first code word be just this code word consisting of zeros. Now, if I'm going to have a one error correcting code, then the minimum distance between code words needs to be at least 2 times 1 plus 1, because here r is equal to 1. So 2 times 1 plus 1 is 3. So I need my distance between distinct code words to be 3 or larger. So why don't I try this as my next code word? Because that code word is of distance 3 from the initial code word. And then what about this code word? That is also of distance 3 from 0, 0, 0, 0, 0. And then the only question is whether these two code words are of distance at least 3 apart. And indeed they are, right? In fact, they differ everywhere except, in the third slot. So here, the minimum distance delta is equal to 3. And that's good enough, according to the previous theorem, to give us an error correcting code. All right, so now in part B, we've received now through our channel this string 10100, and we are to apply the minimum distance rule to compute sigma of z. And, well, okay, which of these 3 code words is closest to 10100? Well, it turns out that the closest code word is this 11100. Right, remember, z is of distance 1 from this code word. And it's further away, z is further away from the other 2 code words. All right, now what about part C? Part C is important, okay? It says, if at most one bit error has occurred in transmission, has a mistake occurred? Okay, so the answer there is no, because remember, our theorem says that if the minimum distance of our code is bigger than or equal to 2 times r plus 1, that is 2 times 1 plus 1 in this case, then if at most one bit error has occurred, then no mistake will be made when applying the minimum decision rule. So the answer is no for the first part. Now for the second part, what if 2-bit errors were made? Well, okay, if we go back to our code and we see, well, what code word, when we make 2-bit errors, could yield this z, that code word is C equaling 0, 0, 0, 0. But on the other hand, when we take sigma of z, we get another code word, 1, 1, 1, 0, 0. Notice that this initial code word that now with 2 mistakes yields our z is then corrected to the wrong thing, namely this 1, 1, 1, 0, 0. So in this second question, the answer is yes, a mistake has been made. All right, now part D is asking us to see if we can find a 1 error correcting code on binary strings of length 5 with 4 code words. So our current code has 3 code words, and we're essentially being asked to see if we can to produce a larger 1 error correcting code. So if we start with our given code, I mean, that might be a good place to begin. Can we add any more code words? And if you think about it a little bit, we can add that code word. So one of the games that we'll be wanting to play is not only producing error correcting codes like this, but making them as big as possible so that we can accommodate larger alphabets. So in the previous slide, at the very end, we were talking about the idea of producing large as possible error correcting codes. So how large can they possibly be? So this theorem gives us an upper bound on how large they can be. So let's suppose we have an R error correcting code. That is, the minimum distance in the code is bigger than or equal to 2r plus 1 on binary strings of length n. Then the number of code words times this quantity has to be less than or equal to 2 to the n. So let's see if we can prove this theorem. So let's start with 2 to the n. So 2 to the n, what's important about that number? Well, that is the total number of binary strings of length n, right? Now that cannot be any smaller, right? It has to be bigger than the size of the union of all of these neighborhoods. Okay, so what's happening here? So remember that given each code word C, we can form a neighborhood of radius r around it. And all of those objects in that neighborhood are binary strings of length n. So if I put all of those neighborhoods together and I count the number of objects in all of them, then I can't get anything any more than the total number of binary strings of length n, and that number is 2 to the n. Now if we go back and we remember the lemma, right? The lemma said that all of these neighborhoods are disjoint. And so if I want to count up the size of this union, it is equivalent, because the neighborhoods are disjoint, to just simply add the size of each individual neighborhood. Now the size of each individual neighborhood, remember, was this. Remember, it was this sum of binary, or of binomial coefficients. So in essence, what we're doing is we're taking this quantity, which is the size of each one of these neighborhoods, and we're adding it to itself a whole bunch of times. Now, how many times are we adding it to itself? Well, we're adding it to itself exactly the size of c times. Okay, so this inequality that is given in the theorem has a name. It's called the packing bound. Now, the bound on the size of this code is often not achieved, right? But it does at least give us a bound. So here we have an example that employs the packing bound. So suppose that Ball State wants to issue ID numbers in binary strings of n bits to 10,000 people with a 1 error correcting code. What is the least value of n for which this is possible? Okay, so these 10,000 people, you can think of them as our alphabet. And so the size of our code, we want the size of our code to be 10,000. Now the packing bound says that the size of this code times n choose 0 plus n choose 1. Remember, in this case, r is equal to 1, is less than or equal to 2 to the n. Now I know the size of the code already. It's 10,000, right? So this says that 10,000 times 1 plus n is less than or equal to 2 to the n. Or rather, that 2 to the n over 1 plus n is bigger than or equal to 10,000. And the smallest n that works by inspection is n equaling 18. So we need n to be bigger than or equal to 18. Now, the value of n that we obtain in this manner is not certain to work. That's because this packing bound may not be achieved. So example 6.22 might be of interest.